Welcome back to Multigrid Methods. We're um, getting close to finishing Chapter 7, talking lately about cell-centered multigrid in 2 dimensions. So we have this rather large section to cover. Um, I've had some thoughts about maybe splitting this up into multiple sections, but it kind of all fits together. It's just a little bit on the long side. So we're first talking about the basics of cell-centered multigrid in 2 dimensions. Um, and I think we've just started talking about the modeling or approximating the Poisson equation in 1D, or sorry, 2D, for the case where the diffusion coefficient is exactly equal to 1. And after that, we're going to get into the case where it's non-constant. So let's see, we're right about here, I would guess. So we were talking last time about the stencils. So we first started out with the description of the Laplacian, or the discrete uh, minus Laplacian operator in the cell-centered finite difference case. Whenever and this comes about from our model equation, whenever the diffusion constant or coefficient is exactly 1, or constant. So we talked about the standard stencil. We also talked about modifying that operator near the boundaries. And if we modify the operator to include boundary conditions, we're going to use this symbol, superscript circ. That means the boundary conditions are taken inside. And I made some corrections to the notes, but I failed to put them in the slides, looks like. So this should be superscript circ and superscript circ. The reason we put those there is because those mean functions that are defined only in the interior of the cell-centered mesh and don't have ghost cells. So let me see if I can remind myself that's a typo to be fixed. I believe it's fixed in the notes. I haven't given you guys a copy of the notes lately, so you can't confirm that one. By the way, so before I forget, I put these updated lecture slides on the Canvas drive, and they're also updated on GitHub. Unfortunately, as I said, with this typo. Now, we talked about how to modify the stencils near the boundaries. One of you asked a good question. That was, how do the stencils modify if you have different boundary conditions, like, for example, homogeneous Neumann? We talked a little bit about that as well. The stencils get modified near the left boundary, the right boundary, the top boundary, the bottom boundary, but then they also get modified near the corners. So this is the modification for the bottom boundary. This is a modification that you need for the left lower corner of the grid. And again, this superscript circ means that I'm adjusting the definition of the multigrid operator, taking, or not the multigrid operator, but the finite difference approximation operator, to take into consideration my ghost cell values from my homogeneous Dirichlet boundary conditions. So last time we also talked about 2 different ways of formulating the exact same problem. So the first formulation was this was the most natural, where I don't modify the stencil, I just tell you what the stencil is. I assume that I'm applying it to a function that has the correct homogeneous Dirichlet boundary conditions, discrete version, and that maps you to a function which has values only in the interior of the cell-centered mesh. I can also, as I just discussed, we can also modify the operator so that it only acts on functions that have only interior values, CL superscript circ, and then of course it maps that to CL superscript circ. So remember, this was my notation for cell-centered functions that have values only in the interior part of the grid and don't have values at the ghost cells. So we came up with this equivalent formulation of the problem, called what I called P superscript 0. That was equivalent. I argued that we argued that it was equivalent to the original problem, which was this. You give me a function, you're looking for a function that has the correct boundary conditions built into the space, not the operator, and satisfies this equation pointwise. So these two problems I claim are equivalent, and not it's not a trivial exercise to show that, but it's I hope feels straightforward. Now, the next thing that I want to say is that we can, once we have this formulation, this one right here, we can turn that into a matrix problem. So this guy is the one that most readily transforms into a matrix problem, or a matrix vector problem. So that's what we do on the next page. So to do this, I need to there's one special thing I need to do, and that is I kind of need to figure out how I want to turn this grid function into a vector and this grid function into a vector. So we talked a lot about that last time. The way to do this, or the time before, is to use what's called the lexicographic ordering to do that. And in that sort of setting, there's I can say the lexicographic way of counting is a kind of most natural way of converting a grid function into a vector. And of course, if I can convert it into a vector, then I can always convert from a vector back into a grid function. Once I know how to do that counting, then this representation here is just NL equations in NL unknowns, and then I can formulate pretty quickly formulate a matrix vector problem out of that. Once I know how to convert that to a vector. So I'm going to leave that as an exercise to you how to do that. It's not it is really trivial mathematics. You just really have to write this out line by line. It's easiest to see if I do a small exercise first, but once I start writing out the equations, I see how this is going to map into a matrix vector formulation like this. I need to do this. I need to, like I said, I need to take F and I'm going to map that into a vector, and I'm going to use the lexicographic way of counting to do that. And so that's what this symbol means. Use the lexicographic ordering to do that. Now, just in case you've forgotten what that means, basically, I have a grid, and the natural way of counting the grid is to use the coordinate I in that direction and j in this direction. Okay? And so in this case, I is between 1 and 4, and j is between 1 and 4. And so to find the value at any particular grid point, this would be, for example, I equals 3, j equals 3, I equals 3, j equals 4, and so on. But I need, when I have the lexicographic ordering, I establish a way of counting these coordinates. And that way of counting is the kind of most natural way of doing it, in my mind at least. I count from the bottom to the top, left to right. So there we go. That's how I would count those 16 cell points or cell-centered grid points. Start from the bottom left and count to the top right. Okay. Well, I suppose you could you could argue, well, you could count this way, right? I could do that. So really, I want to say is I'm going to start at the bottom left, count from left to right, and count from top to bottom. And then that sort of explains exactly how this is done. Once I do that, then for example, f2 comma 2 is just going to be f6, and f4 comma 3, that's that coordinate there, f4 comma 3 is just going to be f12. That's how I convert that function into a grid, or a how to turn a grid function into a vector. Once I know how to do that, then it's just a matter of writing out these equations, and I get a matrix times a vector formulation. So, what does this matrix look like? And what is this matrix? Well, this matrix is the stiffness matrix. It's just a whole lot more complicated than it is in the one space dimensional case. So in 2D, this matrix, this stiffness matrix, is a block tridiagonal matrix, meaning that it has ML by ML blocks along the diagonal and the super and subdiagonal. And then everywhere else, it's zero. The off diagonal blocks in the super and subdiagonals are just minus the identity operator. Okay, so this guy here is just going to be IL is the identity operator, but it's going to be the identity operator size ML by ML. Remember, ML is the number of grid points in either the X or the Y direction. The total number of grid points, of course, is ML squared. Just like this, I can see that is true here. This is 4 points in that direction, and 4 in that direction gives 16 total points. And that's what I called NL. So NL was equal to ML squared, as you recall. So these super and subdiagonal blocks are just the identity matrices. And the only real mystery is, what are these diagonal blocks for this case? So the diagonal blocks, I have to do something special for the first diagonal block and the last diagonal block. And this accounts for the fact that I'm on the top and the bottom boundaries in the way I'm doing the counting. And remember, I had to modify my stencil in particular ways, and the center point always is going to be a diagonal entry in those modified stencils. So, for example, the ones near the corners are going to be 6, the ones on the right, left, and the lower and upper boundaries are going to be 5, etc. That tells me how these blocks are going to come out. So I'm not going to prove this. I'm not going to establish this that these blocks are the way they are. As I said, it really follows from just writing out these equations for a few examples and seeing that this is precisely the structure that you get out of it with these block diagonal matrices. Now, again, the only thing I wanted to point out is these block diagonal matrices are themselves tridiagonal matrices, and they look a lot like stiffness matrices themselves, right? They look a lot like one-dimensional stiffness matrices. This one, the big difference is the diagonal entries aren't quite right. For example, in the one-dimensional case, what was our tridiagonal matrix? It was a matrix that had 3s and 2s on the diagonal. Okay, so it looks a lot like it. It's just not exactly the the same structure. Well, this whole matrix here, again, is an NL by NL matrix. And so remember, NL is ML squared. That's the total number of grid points in this direction times the total number of grid points in the Y direction. So NL is much bigger than ML. So this matrix is a lot bigger. So how many blocks are there in total? So each one of these is ML by ML, and there are ML total blocks. Okay, so there are ML blocks. ML blocks that way and ML blocks that way, right? And so each block is an ML by ML matrix. So that means that the total size of this is pretty big. It's NL by NL. It's getting very large. So I'm going to leave it to you to really establish that and prove that for yourself. It's, as I said, um, not a super hard problem. It's just a matter of bookkeeping. It's really an accountant's exercise, really. All right, now we've gotten, at least for this constant diffusivity case that we're talking about now, where D is everywhere equal to 1. The next piece of the multigrid puzzle is you need to tell me what to do for prolongation and restriction. It turns out that this is much easier to explain via a picture than it is to explain any other way. The other thing I want to say is that it's not a great idea to think about these operators in terms of their matrices. It's much more straightforward to think about these two operators, the restriction and prolongation operators, in terms of their grid representations. In other words, I want to know how these things operate on grids, and I don't really care about what the matrices themselves look like. In fact, you're going to find that we're going to get, especially as we go on in this, the rest of this chapter, we're going to be much more and more uninterested in what these various matrices look like, because the truth is we don't really need to know what the matrices look like. We only need to know what the grid operator representations look like. Well, for the restriction operator, I'm going to show you a picture because I think that says 1,000 words. I have, for example, a 4 by 4 fine grid. Okay, so 4 by 4 fine grid means I have 16. I have a grid that has a grid function defined on it, and that grid function has 16 um, different values. So what I want to do is I want to take that grid function with these 16 values and push it down to the coarse grid to a function that has only 4 values, or in other words, values at these 4 points. So how am I going to get information down to there? Well, for the restriction operator, the most common and the most sensible thing to do is just take the average of the surrounding 4 fine grid points, average them, and push them to the push that averaged value to the coarse grid. So I take the surrounding 4 points, I average them. That means I add up their values and divide by 4, and I push that value to the coarse grid, and so on for all the points. Right? So that's exactly what my little formula here is saying in much more complicated language. I take the values of the fine grid points, I average them, or I add them up, I divide by the number of them, which is exactly 4, and that's what I'm going to set that middle coarse grid value to be. It's precisely that guy there. Prolongation is kind of the opposite strategy, or I have to figure out some opposite strategy. What should I do there? Well, for prolongation, I have a coarse grid function. Let's see, this 2 by 2 coarse grid function has 4 entries or 4 values. Okay, so these are, you should think about there's a number sitting at this value. That's a good way to think about it. And for the prolongation, I'm just going to take that number value and I'm going to map it to these neighboring 4 fine grid points. And likewise here. Okay, I'm going to map those to the neighboring 4 points. So I do that for every coarse grid point that I see. I'm going to look for the 4 nearest neighbor fine grid points, and I'm going to push that value to those. Okay, the same value, if this is 7, the same 7 is going to go to each one of these values. If this is 9, then that 9 gets copied to these 4 values. -1 would get copied to these 4 values as -1, etc. So this is how prolongation and restriction works. Prolongation in terms of the indices that you have, what you want to do is define the values of a fine grid function, for example, VL, from those of a coarse grid function, VL -1. So that prescription that I just mentioned with my picture, okay, taking these values and kind of broadcasting them to the 4 nearest neighbor cell center points, is precisely what this operation is describing. right? So that's the action of the prolongation. So the prolongation matrix, if I wanted to think about it as a matrix, would take a fine grid. Well, it doesn't exactly work that way. It takes a coarse grid vector and maps it to a fine grid vector. So that means that the P matrix has to be tall and thin because it has more rows than it has columns. Remember, NL is should be twice what NL minus 1 is. Right? So the prolongation matrix looks like this, right? Tall and skinny, and the restriction matrix um, is vertically challenged. All right, that fully defines what's going on with prolongation and restriction. And to emphasize a point again, I really don't care what the matrices look like. It's not very important for me. All I have to know is that if I had to get, if somebody threatened my life and made me, forced me to compute it, I could compute what the prolongation matrix looks like. It's just I don't need to do that, and we'll never need to do that. The codes that we're going to talk about next week, when we parade those around, are going to, I hope, convince you of that fact. We really only need the grid formulation. We don't need the matrix formulation. All right, so let's state a theorem that we're not going to prove for the very simple reason that you guys are going to prove that as part of a homework exercise coming up. Well, maybe by next week. So, what does it say? So let's assume that the restriction and prolongation operators are defined the way they previously were, and let's suppose that their respective matrix representations uh, are given by these symbols, and by their respective matrix representations, we mean through the lexicographic ordering. Okay, so you have to be or have to determine those via the lexicographic correspondence. The same with the restriction matrix. Okay, it's understood um, via the lexicographic mapping, and so I should actually in the notes I should add a little bit more about that. So P matrix and R can be found via the lexicographic ordering of the points. So in other words, once I figure out how to map a grid function to a vector, then I can easily turn equations which look like this into matrix vector formulations. That's it. So I just wanted to emphasize that point. I did emphasize the point here for the prolongation matrix, but I forgot to do the same thing for the restriction matrix. It's once you establish for yourself a way of counting to convert cell-centered grid functions into vectors by converting their coordinates, then you're done. All right, so suppose again, after that long speech, that these are the restriction and prolongation matrices that are defined via the lexicographic mappings from their corresponding restriction and prolongation operators. Then we can show four different things. So the four things are um, the restriction operator or matrix times the prolongation matrix is equal to an identity matrix. Okay, that's kind of cool. It actually follows pretty. So this one I'll go back and show you why it kind of follows from the picture that we drew earlier. This one might not be so clear, but once you write out the matrices, it becomes so that the restriction matrix is equal to 1/4 of the transpose of the prolongation matrix. Okay, so that's a very important relation. And then finally, this relation says that the imbalanced Galerkin conditions hold. Okay, imbalanced Galerkin condition holds. So I'm going to have to look this up. Is it condition or conditions for that? I'll say typo, question mark. I think it should just be imbalanced Galerkin condition. So the when we try to figure out if the imbalanced Galerkin condition holds, that means two things. It means that you can compute this and this, but it doesn't necessarily tell you what this value should be. That value is generically what we call R. So this says that the Galerkin or imbalanced Galerkin condition holds with R equals 1/4. So in 2D, I believe it was R was equal to a half here, or sorry, in 1D, it was R equals a half. In 2D, it's R equals a quarter. And in 3D, I can extend this idea, make it go a little bit further. And in that case, it's exactly 1/8. Now, let's talk a little bit about eigenvalues and eigenvectors. And once we do that, then we know how to analyze our method if we're using, for example, something like the Richardson smoother. Well, the good news is you really don't have to do any extra work. The eigenvalues and eigenvectors of the stiffness matrix can be found simply by a little trick, by realizing that the Laplacian operator, if I express it in a certain way, is clearly going to be equal to a finite difference operator, well, to one-dimensional finite difference operator, but acting in orthogonal directions. All right, so what I mean by that is the Laplacian operator acting on a two-dimensional grid function can be thought of as a second-order finite difference going in what looks like the I direction or the X direction, and the same stencil, but going in the J direction or the Y direction. So in other words, I could write this if I had the proper notation already. I could essentially write this as a Laplacian in the X direction, and this one would be a Laplacian or a second order difference in the Y direction. So both of these being one-dimensional. Okay. But I know what the eigenvalues and eigenvectors for operators which look like this, just one-dimensional second order operators, because I did that calculation way back in the early sections of chapter 7, this current chapter. I know that, for example, that if I use a grid function, which is a sine wave, then I'm going to get an appropriate sine wave, then I'm going to get my eigenvalues popping right out. All right, so here's the idea. I'm going to build a grid function, and let's see, this, there's a typo here. No, I guess there's not exactly a typo, but I'm going to change the notation a little bit. Let's use an interior grid function because I only want to define this for interior grid points. Now you'll see that, or maybe I should say that I can easily extend this to ghost cells without any trouble. But it makes life a little bit easier if we simply define these for interior ghosts, or sorry, interior cell-centered points. And then for this guy, let's use the interior Laplacian. Right, so that if I define an interior grid function, I can apply the interior Laplacian because this has the boundary conditions built right into it, and it can act on grid functions that have that property. Then this all makes sense because what I can show is that because of the way of writing this as two one-dimensional operators, one going in the x direction, one going in the y direction, that the one going in the x direction is only going to operate on this guy, and the one going in the y direction is only going to operate on that guy. And each one of those sees that as a grid function, or as an eigen, well, not an eigenfunction, but an eigenvector for its respective for the respective operators. So I'll show you that in just a second. Now, this all makes sense, right? Because this is, yeah, so that's good that I changed that because this makes sense. This is a function defined only on the interiors, and it's equal to a constant times itself, which is a function defined only at interior points. Now, what are the eigenvalues? So the eigenvalues are just the eigenvalues in 1D. As I said, I'll show you this calculation momentarily. And it breaks down in this way. Lambda LST is just going to be lambda LS, the one-dimensional eigenvalue, and lambda LT, the one-dimensional eigenvalue. This one comes from the x direction, and this one comes from the y direction. And I know what these eigenvalues are already because I looked at them earlier in the chapter and I tabulated them. So all I have to do is take those two values and add them together. They were both sine squared functions, and so there's the one for x and here's the one for y. They both were pre-multiplied by the same number here. Well, now the thing I need to know when I'm formulating the Richardson smoother is you need to know what is the spectral radius of the matrix on the particular level that you have. And well, I can find the largest values of both of these guys. They're obtained whenever S and T are equal to ML. And so the largest eigenvalue that I can find is just going to be given as lambda L ML and lambda plus lambda L ML, which gives 2 times lambda L ML, obviously. And the largest eigenvalue we showed previously in one-dimensional case was just 4 over HL squared. So that's why our largest eigenvalue in 2D is going to be 8 over HL squared. And you can probably guess what it would be in 3D because I can do the same trick in 3D. I'm going to get 3 eigenvalues, one-dimensional eigenvalues. Okay, so that would be 3 times that value. So it's actually going to be 12 over HL squared in 3D. I can keep going with this. In any case, I've just found my spectral radius for the two-dimensional cell-centered stiffness matrix. And the reason it works is because I can use the correspondence between the stiffness matrix and this interior operator that I defined earlier, the one with the modified stencils. So the stiffness matrix and this modified Laplacian, which acts only on interior grid functions, are really one and the same entity.
I have a
Okay,
quick
so
question.
go ahead.
So I know that we defined the cell center grid point to be q to the I mean the number of cell center points q to the 2 to the L, right? So the eigenvalue, does it depends on q here?
Let's see. So so your point was ML is equal to Q times 2 to the L,
Yeah, I'm
right?
just worried about if the I mean we don't care about the intermediate one. I'm just thinking about if the largest one will be affected by q.
Q. I guess, yeah, it comes into play, right? Because of how HL is defined. So HL is always equal to 1 over ML. So
Mm-hmm.
it does come into play here, right?
Yeah.
And of course, T and S, they go between 1 and ML. So
Oh,
the
so
largest,
yeah, the Q cancel each other then.
they do, right?
Okay.
Because I just get ML over ML. It
Yeah.
doesn't care what that value is.
Okay. Sorry, I'm just paranoid.
No, that's okay. S times HL whenever S is largest, which is where we get
Yeah.
the
Yeah.
largest eigenvalues, yeah, I do get the cancellation of that.
Okay. Okay.
Right. Okay. So you were wondering, in the interior parts, does it depend on Q or ML or anything like that? Answer is no, but it still is showing up in that guy, right? It still shows up in this denominator. Does that make sense?
Yeah. Yeah. Yeah.
But that's okay. I mean that this is exactly what we expected from 1D and 2D is similar. So as I said, the 2D largest eigenvalue is going to be 8 over HL squared. The 3D is going to be 12 over HL squared, right? So it scales like that. And if you're interested in high order Laplace equations, I guess we can theorize that the largest eigenvalue is going to go like d times whatever the dimension is times 2 over HL squared, where d is the number of dimensions that we have. Right. So what is the trick that I'm applying here? It's very basic, I think, and uh, but it's basic. But let's go ahead and calculate it. So the idea is the 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 analog is exactly what you do in one space dimension, right? So you just realize that minus Laplacian of w, right, is equal to minus the second derivative of w with respect to x minus the second derivative of w with respect to y, right? But now if you say w is equal to sine, let's see, what did we say it was? It's going to be sine s pi, roughly, sine s pi x and sine t pi y, right? So then if I plug that in, then minus Laplacian w is going to be for the x derivative, the y derivative doesn't play any role, so it's going to be minus sine t pi y. And what is the second derivative of w in that case? It's going to be uh, the sign changes, right? And then we get sine squared pi squared sine s pi x. Probably shouldn't have changed the order. Plus the same sort of thing, right? So when I do the second calculation, it doesn't care about this term. It only cares about that. Treats it as a constant. And so I get what? Sine pi squared again and sine t pi y. So I can see that I can do some manipulation here, right? Because I can pull out 2 sine s squared. Oops, I made a mistake here, right? So this should be a t squared. 2s squared, or no, should just be s squared pi squared plus t squared pi squared times w, right? So it's the analog of what's going on in the continuous case. The only difference is in the continuous case, my eigenvalues are a lot simpler than they are in the finite difference case. But the calculation is more or less exactly the same. So a I have a finite difference operator that is going to act on a function which looks like that, and I'm going to write it as minus Laplacian in the x direction WL minus Laplacian in the y direction WL. And again, the same thing happens. This is a linear operator. It doesn't care about, for example, this guy only sees the y direction, so the x direction can be treated as constants and vice versa for here. So that's why this eigenvalue calculation is so easy to do. I really don't have to do anything more than just recognize that this operator can be written as the sum of two one-dimensional operators, one going in the x direction, one going in the y direction. Right, okay, so that takes care of the eigenvalues and the eigenvectors, right? So those are our eigenvectors and these are our eigenvalues. Now you might object to that. You might object to that, right? So is that this function here isn't a vector, right? Well, again, I can always take any grid function and I can convert it into, or yeah, grid function, and I can convert that, right? It has values for each I and j for every s and t that you choose. And these are my cell-centered coordinates, by the way. These are the cell-centered coordinates in the x and the y direction that I defined way back somewhere around here. So this is not a vector, but I can easily turn it using the lexicographic ordering into a vector. So I'm never going to make a distinction between a grid function and a vector. Through the lexicographic ordering, I can always change one into the other and the other into the one. That's the basic idea. So eigenvalues are tabulated. The eigenvectors are tabulated. They basically come for free by knowing what I know about the one-dimensional problem. As I said, if I want to do a three-dimensional Poisson equation on a cube, then I have nothing more to do uh, there either. I can still use the one-dimensional case and just use the fact that my finite difference operator can be broken up into the sum of three one-dimensional operators. Again, the analog is it's an entirely analogous to what happens in the continuous case, which we did here with this little calculation. So all the ingredients now are in place to implement our standard multigrid algorithm. We could do Richardson smoother. You know how to establish a Richardson smoother, even though we didn't talk about that very much. Um, we we know how to do restriction prolongation. What else? We know everything we need. We know that the imbalanced Galerkin condition holds. So we can implement our multigrid operator or multigrid solver in 2D now. The question does it work? Does it converge? Is it useful? Well, we're going to do some computational tests later on, maybe next week. I hope we're going to run some code and test these things out. And I'm going to really try to impress you by showing you calculations where we have, let's say, millions of degrees of freedom, or so basically we're solving a matrix vector equation where the unknowns are in the millions, tens of millions, maybe even hundreds of millions. So you'll want to show up for that, I think. So all of the ingredients are in place to implement these things. The question is, do they converge? And the answer is yes, they converge uh, rapidly. In fact, now we can the next step would be to show, because the smoothing property is going to be fairly simple. The next step would be to show that the alpha weak approximation holds where with alpha equals a half again. So I didn't say it here in the notes, but we can do that again. We can show that the alpha weak approximation holds with alpha equals a half. How do you do that? Well, you just mimic what was done in the one-dimensional proof. You don't have to do anything kind of super new. You just follow the prescription of things in the one-dimensional setting, and you can show this. Alpha weak approximation property holds with alpha equals a half. We're not going to do that to save time. It's enough to know how it was done in one-dimensional case. That's basically all we have to say about that. Once you have the theory from chapter 5, then and you show these things, like for example the alpha weak approximation property, Then we know that the W cycle converges. The W cycle multigrid method was established, the convergence of that was established in chapter 5. And so that's a freebie for us. We don't know if the V cycle converges. That is still up in the air. The V cycle convergence is still an open question in this setting, as far as I know. But we will know that the W cycle methods, multigrid methods, converge with the contraction factors which are independent of the number of levels. Okay, so that is all completely done for us. The convergence question, at least partially, is answered. The next topic that we want to discuss is what happens whenever our diffusivity is non-constant. So this is the case of variable diffusivity that we talked about in the one-dimensional setting already. So for example, we want to find an approximation to this problem, right? Not exactly though. Insert a gradient there. Okay. So what if D is non-constant? What do we do? Well, actually, we can use what we already know from our one-dimensional setting and do what we did previously, or what we just talked about, I guess. We said an operator like this can be thought of as an operator with two pieces, and that's still true. So this is going to be minus d by dx, d d u dx, and then the same in the y direction, minus d by dy, d du dy. Okay, so two operators which are both more or less one-dimensional, and I have approximations for these guys already in the one-dimensional setting. So I already have an approximation for this guy in particular and this one as well. So if you remember, in one dimension, if I had the variable diffusivity case, then for the x derivative, I used that approximation. This is my analog to the 3-point stencil for the Laplacian operator, but where we have the diffusion being non-constant. So remember, I said there we were going to write this part here as the finite difference of a function times a finite difference. So basically, we take a finite difference and a finite difference, evaluate them at two different points, multiply by a this diffusion coefficient, and then take the finite difference of that. So I'm taking two finite differences, and the result of that is that I get the HL squared in the denominator. And I do the same thing in the y direction. So I already explained this in one dimension. It's no different here in multiple dimensions. The only weird thing is that I have to be a little bit careful about where these pieces here are defined. So maybe it's worth writing that out, making a picture. The idea is I have a grid where, that's not right. Okay. I have a grid where I have a mesh and, well, cell-centered mesh, and I have defined on that this grid function u. So the grid function u lives at these points. These are the so-called cell-centered points, and maybe even I have ghost points for this function as well. I don't know. Remember, we can always get rid of the ghost values. We can keep them when they're useful to us. We can get rid of them when they're not. So what I need to do is I need to create a stencil. Let's say I'm evaluating at this point. So remember the 5-point stencil, how did that work? I needed to sample these nearby points, right? 1, 2, 3, 4. And the reason why I did that is basically I was building a one-dimensional Laplacian in two different directions, an x direction and a y direction. So the x direction Laplacian went that way and the y direction went that way. And that resulted in this 5-point stencil. But now let's think about what's going on in this non-constant diffusion case or variable diffusivity case. So what I have is, for example, I want to calculate this approximation. Okay, I want to calculate an approximation at a point ij, right? How do I do that? Let's kind of focus on what's going on here and here. So at a point ij, I'm trying to come up with this cell-centered finite difference approximation of this complicated operator. Well, I've already said I've got to break this into a one-dimensional difference and another one-dimensional difference, but going in the y direction. Let's look at this guy. It's the difference of a difference. So how am I going to calculate that? Well, the difference in u is pretty easy to get. It's, let's say I want to focus on these 2 points first. And let's use purple to take the difference. Okay, so for the first difference, I'm going to take these 2 points, say, and I'm going to subtract them and divide by HL. So let's suppose this mesh point here is I and J. So this guy here must be I plus 1, right? And this is I minus 1. So what would the difference be if I took these two, the difference of these 2 points? It would be VL I plus 1 J minus VL I J, and I divide by HL. Okay, so that's a difference for those 2 points. And I'm gonna naturally think, to get second order accuracy, I'm gonna think about this point being defined at that, or this difference defined at that square point. So that square point is what we call an edge point. This is called an edge point, right? That makes sense. It's a central difference with respect to that edge point. If I do the difference of this value minus that, divide by HL, that becomes a second order approximation of a derivative. But second order only if I understand it as being the value at, if I understand the value of this difference being defined here at this edge point. Okay. Same thing is going to happen over here, right? If I take the difference of these 2 points, then that ends me up here at this purple point. So how do I count that purple point? Well, that's going to be I minus a half. And this guy here is going to be I plus a half. Okay, let's get rid of our ghost points. We don't need them. Just add some distraction. All right, so I minus a half, I plus a half, and I, of course, is right here in the center. Same thing with this point here, J, and then we have J minus a half, J plus a half. And J is right there. Right, so now let's, again, so for this difference, we're taking the difference of these 2 points and we're deciding that its value is going to end up on that grid point there, which is called an edge point. Let's do the same thing, but use a different color in the y direction. I'm going to take this point minus the value at that point, and I'm going to define its value at this point, which is called an edge point. What's the coordinates of that edge point? It's going to have I coordinate being I, okay, or its x coordinate is just I, and its j coordinate or y coordinate is going to be j plus a half. So this is the point ij plus a half. What about this point down here? Well, this point down here is where my next difference is going to be defined, and it's going to be the difference between the value at this point and the value at that point, and it's going to be defined at this edge point, and its coordinates are I equals, or just the x coordinate is I, and the y coordinate is j minus a half. So that's where I want to define the values of my diffusivity. I want this diffusivity to be defined at least at these 4 points, right? And let's give them their coordinates. So this coordinate over here is d I. Well, I probably put L there. I plus a half and j. And this guy here is dl I minus a half j. This point is dl I j plus a half. And this point is dl I j minus a half. Those are the 4 points. So those are exactly the points that appear in my approximation. There's dl I plus a half j. That's this guy right here. So all I'm doing is finding out what is the diffusion coefficient, not constant, but the diffusion coefficient, and I'm going to multiply it by the difference, which I just found there. That's that difference. Okay, I'm going to do the same thing for the difference at that point. I have to multiply that diffusion coefficient times the difference there. And then I take the difference of those things. Finally, to get my full approximation in the x direction, I have to take the difference of this guy, and that lands me back at that point. Same thing here. I take the difference between this point and that. That gets me to the edge point. I multiply by this d value. Do the same down here. This point, keep accidentally hitting my eraser. So I take the difference of those 2 points to get here, multiply by that diffusion coefficient, and then I take the difference of the values at those 2 points to get me back there. So that's precisely what's going on with those 2 calculations. So again, it's just a finite difference of a finite difference. Doing 2 finite differences in each direction results in the division by HL squared in both cases. And that's basically the description of this operator. Okay, now the operator, we're going to give the same nomenclature and naming convention as we had before. The fact that it's defined on level L is going to be indicated with a subscript. The fact that it's non-constant is just going to be indicated by the fact, or by the superscript D. What we can do is the same sort of things that we've done before, and we can get rid of, we can modify the stencil um, near the boundary and near corners. Now this stencil is a whole lot more complicated than the typical 5-point stencil. Remember the 5-point stencil was 4 minus 1 minus 1 minus 1 minus 1. Right? That's nice in a world where the diffusion coefficient is constant, but it gets a whole lot more complicated whenever it's non-constant. So we can still fill in these numbers, but each one of these numbers is going to depend sort of in a complicated way on the diffusion coefficient. So we don't even bother doing it. We just simply don't write the stencil anymore. So when I say modify the stencil, I didn't even tell you what the stencil is, but you should be able to picture what it could be. And so when I say modify the stencil, well, that means obviously I'm going to do something slightly different near the boundaries because I need, if I want to build the boundary conditions into the operator. All right, now how do we define this variable diffusivity? It's a level dependent thing. Well, in one-dimensional case, all you ever did was you just sampled the diffusion coefficient at the appropriate edge point. In 2D, because we want to, it's a bit harder to satisfy this imbalanced Galerkin condition if we're not careful. We have to do something a bit more complicated. So in 2D, here's the algorithm that you have to employ. So at the highest level, the top level or the finest level, that corresponds to L equals capital L. Then what we do is we sample the diffusion constants at all of the edge points. So this is exactly what it's in words exactly what I said in pictures and even in symbols. So here's the picture. I know the diffusion, if the diffusion constant is defined over the whole grid, over the whole domain, then certainly at any of these points, I can sample the values and define the diffusion constant there. That's exactly how I do it on the finest level. That's exactly how I do it on the finest level. Whenever L is equal to capital L, all I do is I have some function laying around and I'm going to find out what its value is at that point, and that's going to be copied into that value there. And what's the diffusion constant at that point? Well, whatever it is, I'm going to copy its value into there. Remember, the diffusion coefficient had to satisfy a couple of conditions. It had to be positive, it had to be bounded below by a positive number, and it had to be bounded above. The easiest way to take care of this is just say it's a continuous function on the whole domain. And remember, every continuous function achieves its min and its max. As long as its min and its max are strictly positive, then that's all you need. So at the finest level, I simply sample. Okay. Sometimes this is called a continuous to grid projection. You just pull in the points that are defined everywhere, and you're going to sample them at certain grid points. And you're projecting the continuous values into the grid. Now, for the lower levels, we have to define them recursively from the upper levels. We have to define the lower levels recursively from the upper levels. Otherwise, if we don't do it like this, then the Galerkin, the imbalanced Galerkin condition is not going to hold. So let me not explain to you what's going on with this formula because it's fairly complicated, and I'll only tell you what's going on with a picture. Okay, so the picture is worth 1,000 words in this case, maybe more. So the picture is of the following situation. Suppose I have a two-level grid and I've defined the diffusion constant on the upper level, and now I want to get it down to the lower level. This operation is what's commonly called a prolongation, but it's not a prolongation in the same sense that we had, or sorry, it's not called a prolongation, it's called a restriction. It's not a restriction in exactly the same way or sense that we restrict self-centered functions. It's a little bit different. So here's the idea. Okay, we've got to have at least two levels to work with. So there's the coarse grid. So on the coarse grid, I need to define, let's do orange and red points to keep things interesting. So I need to get the diffusion constant defined at all of the edge points. So these are what I call east-west edge points. Okay, they're on the east and west of each cell, east-west edge points. I also need to get the diffusion defined on the north and south edge points. So here's a north-south point. There's another north-south point. Okay, so I need to get the diffusion constant coefficient. I'm never going to get this right, and I apologize. It's a diffusion coefficient, not a constant, defined at these 12 points that you see. But I need to use the grid values at the finer level to do it. So now let's suppose that on top of this is a fine grid. So the coarse grid is 2 by 2. The fine grid is going to be 4 by 4. Now on that guy, I'm going to have these unfilled circles. I'm going to have diffusivities defined at all of these points. All right, so there's going to be, what do I have here? 1, 2, 3, 4, 5, and 5 times 4. So 20 points here. I want to distinguish the unfilled points from the filled points. So the ones on the coarse grid are filled. The ones on the fine grid are unfilled. So if the diffusion coefficient is defined at all of the edge points on the fine grid, then it's defined at all of these open circle points. Let's go to the east-west points. The east-west points for the fine grid are going to be as follows. And again, let me first go in and color in the ones on the coarse grid because they should be distinguished from those in the fine grid. So on the fine grid, I have the flux, or sorry, the diffusion coefficient defined at all of these open circles. And so there are 20 open circles on the east-west edges and 20 on the north-south edges. So the question is, what's the correct algorithm for getting the values to the filled red and the filled orange points? Well, it turns out to satisfy the Galerkin, the imbalanced Galerkin condition that we want to satisfy for our method, and that's certainly something that we want to satisfy, then what we have to do is, for example, if I want to calculate the value of this guy here, I guess I'll use my highlighter. Let's use bright green. Okay, suppose I want to fill that point knowing what the values are at these fine grid points. What do? All I do is I'm going to average those two values. Okay, simple average. Just take the sum of the two values and take half and put the value of that average in that point. Now I don't need a diffusion point at here. I don't need a diffusion coefficient at that point. I'm going to skip over that. I don't need to take that average. I'm going to go on to the next one. I'm going to take the average of these two guys and put its value there. Skip that one. Take the average here and put it there. Okay, same thing here. Skip, take average, skip, take an average. So that takes care of the east-west points. How many calculations did I just do? I did 6 averages. Some points I'm throwing away entirely, and that's because I can show you later on that you're not going to need those. What's the next step? The next step is to fill all the red points, right? So the red points, and this one I want to, there we go. Just want to make sure we're clear what points are on the coarse grid and the fine grid. So the coarse grid are these 6 points which are unknown. I want to use the values at the fine grid to fill those in. So I'm going to do the same procedure. I'm going to average these two guys, skip over those. Those are just going to be thrown away. Average here, skip, average, average, skip, average, skip, average, right? Does that make sense? Now, the procedure should make sense, and that's exactly what I have listed right here. Okay. I'm using the fine grid values averaged at certain points, and this average here is done in J, so it's going to be an east-west average. And same with this guy. And so this is going to give me my 2 new east-west points, and this is going to give me my 2 new north-south points that I'm going to use when I show you the diagram on, not the next page, but the next one. So this is complicated, right? How do you Why is this important? What's the use of it? Doesn't seem to make sense. Well, that's why I just told you what's going on here. So a diagram shows a bit more easily exactly what's going on. The points, how do they travel? Well, information is going to travel this way, right? If I put little arrows on that, that average travels that way, right? And now this is why I call this recursive top-down filling procedure, recursively defined diffusivities going in a sort of top-down procedure. So what was my exact phrasing there? Yeah. Recursive top-down variable diffusivity. You define it on the finest level, and then at the coarse levels, you're going to use the fine level information, for example, level L going to level L minus 1 to fill the coarse levels. So the procedure is explained right here through this nice picture. I wish I could just turn this picture into a tick-Z plot. Hint, hint to you guys out there. Right? This explains exactly what's happening with these formulas. Now, the last thing I want to point out is this next calculation that I'm going to show you is that the Galerkin imbalanced Galerkin condition holds. And of course, in the 1 minute that we have remaining to us, we're not going to be able to do this today. But the idea is I need to think about if I have information on a fine grid. The fine grid is this guy here, and the cell-centered points of the fine grid are the red points, the filled red points. I'm going to use information at all these red points to check that the imbalanced Galerkin condition holds. When I do this, I'm going to be thinking about where and how these diffusion coefficients appear. Okay, so we're going to refer back to this diagram a lot in the proof that's coming up. So this proof here. But that's about all I can say in foreshadowing what's going on. We really want to prove, let's see, why are you stuck? There we go. I want to show that the imbalanced Galerkin condition holds even in this really complicated situation, the non-constant diffusion in 2D. I want to show that this imbalanced Galerkin condition holds. So I need all of this notation and I need this understanding about how the diffusion constant is defined or the diffusion coefficient is defined at the coarse level. So that's kind of foreshadowing where the discussion is going and what we're going to do next time. So I'm going to stop there and we will take your questions. You can turn your cameras back on. Are there any questions or comments? This figure, I need to get this figure into the book because I think that really explains nicely how the restriction, which is defined through this procedure for the diffusion coefficient, how that works. And again, the reason why I'm bothering to do this is because if I don't do that, then there's no way I can be guaranteed that my imbalanced Galerkin condition holds. And if the imbalanced Galerkin condition doesn't hold, then I have no hope on earth that my multigrid method can converge. So, well, at least theoretically. It turns out that how I define the diffusion coefficient on the coarse grid doesn't matter too much for practical purposes. In other words, you can do it 10 different ways and it's still going to converge and converge quite rapidly, in fact. Um, you know, and I can show you tests of that. But if I want to prove theorems and I want to prove that it actually works, then the only hope that I have is that the imbalanced Galerkin condition holds. So that's why we've done all this extra work. Anyway, you may or may not care about that. Some people do, but But any questions, no matter what, whether you care about it or not. Questions or comments?
I have one quick question.
Okay.
Can you go back to the one that you wanted to prove, like the imbalanced Galerkin condition, that statement?
Here.
Uh,
Oh, the thing that I
no,
asked you guys to
yeah, yeah, yeah,
prove?
yeah,
Okay.
yeah,
So that's where was it? Maybe somewhere around here.
yeah, yeah, yeah. So I understand the second and the third matrix equation. The first one, the
Yeah,
RL minus one times PL minus one equals to IL minus one. I also understand it conceptually because you do prolongation first. So you copy all these
correct.
values and then you
Correct.
restrict it. And then the average of four identical value will definitely equals to the same value. But
Yeah.
does it impose any like theoretical importance on this particular equation?
As far as I can see, it has no it doesn't seem to have any theoretical importance.
Is it just like sanity check, kind of?
Yeah, right. This actually holds in any dimension as long as we
Mm-hmm.
keep, remember, we kind of defined this restriction and prolongation in a kind of analog way to what we did in 1D. And so if we keep going in this way of doing it, we could do this in 3D.
Mm-hmm.
We're going to get the same thing.
Okay. Okay.
Okay. Um, so yeah, I guess for me it's a kind of sanity check.
Mm-hmm.
In you you know you hit it right on the head. If you do the prolongation first, you push four values from this point outward, and then if you do restriction right after that, then you average those 4 points, which are exactly the same, and you get right back to the same point value. Like for
Mm-hmm.
example, if I have 7 here, I'm going to push 7 out 4 ways, and now these new values are going to be 7, and then I take those 4 sevens and I average them. What do you get? You get 7. So that's exactly what you were saying.
Mm-hmm.
Um,
Yeah.
you you do prolongation first, then restriction. You get the same value. That's the proof that you have the identity here.
Yeah. Yeah.
Yeah, that's exactly right.
Okay.
And now I didn't show you how to do the proof for this case. It's an exercise, right? But the proof that I'm going to do for the more complicated case can serve as a proof for this case. Why? Because the proof for this case is just D equals 1. This is just the D equals 1 case. And I'm going to show you how to do D not equal to 1, which is much harder, right? But it really does serve as a proof for this guy, or at least this part here.
Got it. Thank you.
Yep. Any other questions?